Great. Thanks, Kiana. And I appreciate everyone tuning in for this session. I hope you're having a great conference so far, and I'm sure the rest of it will be fantastic as well. So let's jump into this. My name is Brent Laster, and I have a company called Tech Skills Transformations, LLC. And today's session is about containers in depth, understanding how containers work to better understand or to better work with containers. So just a little bit quick note about me. As I said, I have a training company. My day job is as an R&D DevOps director at a company called SAS here in Cary, North Carolina. Do quite a bit of training, information on social media, connecting with me. If you'd like to do that, feel free. Also have a couple of books out there, one on Git, if you're interested in learning more about Git, either someone who's fairly new to it, or if you have been using it for a while, I think you'll find something useful in that book. If you're interested in CI/CD pipelines using Jenkins pipelines as code, check out the Jenkins book. If you do happen to get this one, would suggest maybe getting the electronic version, since the printed version has some screenshots that are kind of washed out in there. Also do a lot of training on O'Reilly Media. Don't say this to say anything about myself, but just to let you know, there's a lot of training. If you happen to be an O'Reilly member out there, you can search for things about Kubernetes. I know Brad was just doing a great presentation on Kubernetes prior to this one. Letting Kubernetes get all sorts of fun things. Just search for my name and you'll see what courses are being offered out there. So in our short 45 minutes that we're going to talk about today, we're going to try to cover these sets of things: what containers are and what are the benefits they provide, how they're constructed, what makes up, what are the components that go into them. We're talking about things like layers, images, and we'll explain what those mean. What does immutability really mean? Often we hear the term that containers are immutable, and people get confused about that meaning that things can't be changed at all in them. So we'll clarify that and try to move some of the mystery there. We'll talk briefly about some of the core Linux functionalities containers are based on. Container technology has actually been around quite a while, the underpinnings of it in the Linux operating system in there. And then companies like Docker and such have built on top of that. So we'll give you just kind of a very brief sort of below the surface, what's going on with them. We'll talk about how containers can reuse code. We'll talk a little bit about storage drivers, those mechanisms that on the operating system help to chain everything together to allow us to actually create containers. And we'll look at one in particular, the overlay 2 storage drivers, and then we'll touch on the open container initiative. So a lot of content to try to get through in 45 minutes, probably 40 minutes, I guess, actually, maybe a few minutes for questions. So let's jump into it. So what are containers? So a couple of ways to define a container. A container could be thought of as a standard unit for delivering software with a virtual environment to run it in. It can also be thought of as functioning like a fully provisioned machine with all the software needed to run for a single application. A lot of times I'll tell people, think of a container almost as being like a laptop or a standalone machine with just the things for one particular application needed to run on it. Then this is the idea with them, is that they get everything packaged in there. Whenever it's a way of packaging up software. So in addition to having the whole environment and the application to execute inside of that environment, we also are able to use this packaging format, this container packaging format, and particularly container images, as a way of sharing these environments, just as if you were going to give somebody a laptop that had everything already installed on it to run that particular application. You could do the same thing with a container image. You can point somebody to a container image and they can execute the application in there and have all of the environment already set up and running with it. Whenever you talk about containers, you're probably going to see this obligatory picture of a cargo ship, a container cargo ship, with the idea that containers being like those boxes on those cargo ships where everything is stored inside. And if we want to think about what's actually in a container, if we use the analogy of this sort of cargo container, we have things like the application itself, the runtime environment for it, the dependencies that it needs, the settings it has to use, the configuration, system libraries, system tools, all these pieces inside of that one self-contained environment. So a container, though, is not a VM. A VM is a virtual machine. It is basically a way to emulate a computer running through what we call a hypervisor, or another application that runs on top of that. And you'll hear the two terms used a lot, but there are different concepts there. A container is actually, instead of being a separate instance of something running, it is really carving out operating system resources, allocating portions of the operating system in such a way that those portions seem dedicated to the application. An application running inside of a container thinks it has its own machine, its own system that it's running on, but in reality, it's getting a carved out portion of the operating system resources so it can do what it needs to do. Containers are running instances of images. So at the highest level, we talk about the containers, but containers are based off of images. We're going to give you an analogy in a few minutes to kind of help you understand a little bit more about this. But images define what goes into a container, and containers are built from images. So what are some of the benefits of containers? Well, if you think about being able to have this image or this container that you can transfer easily and that already has everything set up to run an application, it's a very convenient way to share an application with its environment to run. You don't have to go through the process of trying to install software, provision things to get it going. You just get it and take it and run it. The best practice, continuous development, integration, deployment allow for frequent, reliable builds and deployments. Meaning once I have the container defined or I have the image defined that I can base the container off of, I can go off and deploy that on any kind of system that can run something that can run the containers like Docker. It's quick and easy rollbacks due to image immutability. What we mean by that is that images, once created, the images themselves don't change. So if I need to get back to a previous version of something, I can just roll back to a previous version of the image. And since the image, again, has everything it needs, it's easy just to go back and run the older version of those kinds of things. So there are lots of other benefits on here, but the main thing is that these are portable and they allow us to focus on developing the application and running the application instead of having to worry about all the infrastructure provisioning and setting up all of the infrastructure for this each time, because the infrastructure or the environment is kept with the application inside of the image. So we mentioned this term image. What is a container image? Well, it's really a read-only template used to create a container. It's sort of like a snapshot of all of the configuration, the environment and stuff that we need to run the application. One way I tell people, an analogy to think about this with, I think is handy, is think about an image on your computer. If you have ever provisioned a computer for someone, whether it's part of your job, whether it's part of your role as a tech support for family members or friends or whatever, you've probably gone through this process of setting up, installing software on a new disk for somebody for a computer, installing the operating system, installing the applications they want, those kinds of things. And what you end up with is an image, a collection of software, a collection of configuration, and the environment you need to run things, all stored on that disk as an image. Same idea with the container. We can provision everything, we can set that all up, store it as an image, and then when we actually need to use it, we can spin up a container from that image. Now, images themselves are generally considered to be what we call immutable. And again, that word typically means they don't change. So we'll talk about how containers use images in a bit, but the basic idea is once I provision, get everything set up on an image, if I need to go to a new revision of software or a new version of something that needs to go in the image, I create a brand new image with that update in there. I don't update the existing image, I create a brand new one. Images are stored in registries. So we have for our images for containers stored in registries, which are like a repository. You'll hear things like the Docker Hub. So we can go out to Docker Hub and we can find an image that somebody has set up that has a version of, say, Ubuntu already set up with it and a version of MySQL already provisioned on it. And we can get that image down with the operating system with MySQL, and we can start up a container then, and we can be up and running with a MySQL environment in a matter of minutes after we download the image and spin it up. Container images are built up from layers. So images are like the images we have on the disk of our computers that are sitting there until we turn the computer on. They're still just sitting there. They're not necessarily running, but they are available to us. We have everything set up. When we turn the computer on, then we can use it and start running with it. But images themselves are built up from what we call layers. So an image layer is really just a series of some either configuration or maybe some files put in there, or maybe even another image that's in there. So a Docker image is built up from a series of layers. We talk about Docker a lot in the context of containers because Docker is the most well-known application for managing containers. There are lots of others now, as we'll talk about later on in the class. But basically, what we have when we start creating this image that will eventually allow us to spin up a container from it is what we have called the Docker file. Now, a Docker file you can think of as sort of a recipe or a checklist. Again, kind of equating this back to the idea of provisioning a system for someone. You might think of this in the context of if you were setting up a computer for somebody and they gave you a checklist and said, I want Windows on it, I want Microsoft Office, I want Norton Antivirus. You have a set of things on there. They may even say, I want you to copy some files off of a USB drive onto there. Same idea with the Docker file. The Docker file serves as this sort of recipe or set of checklists for things to go into this image. You can see on the right-hand side of this slide, we have a simple Docker file that says starting out with the from command, from Ubuntu 18.04. What that means is we want to start out building a new image based off of an existing one that has Ubuntu, the Unix operating system on it. So we're going to grab that image. That becomes the first layer, the first level of software that we lay down in our image. Then we're going to copy some things over from a different directory, from like an app directory that we have, and maybe we're going to run some things and run some other scripts and stuff to create content on there. But it's that same idea of installing software onto this image to create these different layers in there. Ultimately, all the layers together make up that image that we can use to run applications in and run our containers. Usually your base layer is just an operating system image. For example, you might have, as I said, one that's Ubuntu, and if you were using a MySQL image to run a container from, it might be one that somebody had put together and they put down an operating system lowest layer, then they configured MySQL on it and provided whatever environment that's in. So you can have base images, which are simply things like operating systems. You can have base images, which are running applications. You can have base images, which serve as like clients for other ones. Anything you can typically run on a regular computer, you can put into a container image and spin up a container to use it. Now, when we talk about the image proper, we're talking about the set of software that's been set up and provisioned on it. When we talk about a container, really all a container is just adding a very thin sort of read-write layer on top of that image. So we are basically setting up an area for us to work in. If you think of our analogy of talking about provisioning a computer for someone, we set up all the software on there they're going to be using. We create the disk image with all the things on it. And then we eventually create like a user space, a home space or a home directory and such. Now, the user is typically not going to be making changes in that operating system area on the disk where we install it or the applications, right? That's where we talk about the immutability. Generally, we're not going to be making changes in the underlying software, but we do have an area that is set up for things to be written into, for users to work in, for applications to write things to if they need to. And that's what happens when we take an image and turn it into a container. All we do is shown on this screen is just put a thin read-write layer on top of it where we can do our work. And all the changes that go into that container are actually going into that thin read-write layer. We said earlier that containers are different from a VM. If we have a virtual machine, as on the left-hand side here, we will typically have our server, we'll have our host operating system, and then we'll have some kind of a hypervisor. Hypervisor is a fancy word that simply means an application that can run on our operating system and then allow another virtual computer to run on top of that. So it's a hypervisor that has to then host another operating system in there, and then the applications on top of that. On the right-hand side, we talk about a Docker environment or a container environment. What we're really talking about is that we have Docker or something like Docker installed on our operating system. And then that application knows how to get portions or carve out portions of the resources from the operating system to be able to allocate them or to group them together so that an application can use those portions of things as its own environment. So in the one hand, the virtual machine has an extra layer, a couple extra layers in there of a program, the hypervisor, to be able to run it, to run the virtual computer, whereas Docker is very simply carving out portions of the operating system resources and treating them as an individual environment for an application to run in. So I'll start a little run here that shows you running a Docker command to actually take this Docker file, this input file, and to build an image from it. And let me explain what's going on. On the left-hand side there, you'll see that we have a Docker file that starts out with downloading a version of MySQL. So this is an image that somebody else has created, which has a version of an operating system and then a version of MySQL on it. And they've set it up so that we can start this image as a container and we'll be able to have a MySQL to run with. Now, what's happening here when we do the Docker build, the build is the command in Docker that says, go and look at the Docker file and do all the steps it says to create the image, to create the various layers. As you can see here, what's on this and running on the screen, it's actually getting the various pieces, the various layers of this base MySQL image down. It's expanding them and it's creating a layer. And then it goes through the other steps in our Docker file. It goes to copy some stuff into a local area from a local environment. It sets up what's called the entry point in the command. These are the things, this is how what Docker is going to run or what the container is going to run when we start it up. And you can see, if you look on the black box here on the right-hand side, we have a number of different steps that have executed, and each one of these has effectively created a new layer in the image we're building. In fact, if we were to go through and look in a little bit higher level detail of it, we could see that if we were to go and run like a Docker history, and Docker history would allow us to see all the different layers that went into the images. The top 3 or 4 layers there are ones that we just created. And then the ones that say missing out to the side, those are all of the layers, all of the operations that went into creating that MySQL base image. So those are all the pieces that somebody did to go through and create that. And if you look closely at them, you can see they just were doing things like adding files and updating, getting packages and so on in there, making directories and so forth. So it's the same kind of operations that you would do if you were installing MySQL yourself. It's just somebody's already done it in this image environment. It's packaged up as a base image, and we can use it to build on from there. So in this case, if we look at the instructions in the Docker file, we can think of each one of them as basically constituting a layer that is in the image that we are creating. So we are basing this off of a MySQL base image. We're adding on some special files that we want to have to customize some databases, set up some stuff for us. And each one of these commands in the Docker file will usually translate to a layer in the underlying image. Now, when I say each one translates to a layer, it used to be that it was automatically given that every command in a Docker file would create a new layer in the image. But these days, they've got a little bit more efficient about it, so it doesn't have to be that every command doesn't necessarily translate to a layer. These layers are stored within a Docker area on your disk, and the setup they have in them, the commands, the files and stuff are stored there. And then Docker and the device drivers know how to chain them together to produce this image that we want to use for our container. So we've got this image now. And layers are basically like files to the OS. You can almost think of it as being like a path variable. We talk about a path variable in the operating system where we have a set of directories chained together. Same kind of idea. It's a set of things that are chained together to make up this environment that we want. Now, the image layers are read-only. Here's that word again, immutable, meaning that we can't make changes in the content of those levels. And if we want to create a container from this image, the actual container, we can do the Docker run command. This again is in Docker, but the other applications that manage containers and images have similar kinds of commands. So we do Docker run, and we're actually passing a couple environment variables. If you look in this black box here in the center, you can see the -E. we're actually passing in an environment variable for a MySQL root password. Not the most secure thing in the world, but a lot of times images will be set up to accept environment variables to pass in information. Now, what happens when we do that? Well, if you notice here, we have this white layer, this thing that has this funny characterization in CCAE. That's just the identifier of that layer. But when we go to run this, we take the image to make it into the container. We're simply adding that thin read-write layer on top there. And that means that that is a place then that we now have a container running. So we have the container running based off of the image. The container just provides an area for us to work in, or for the application to work in. Now, one of the things that makes this all work together, there are a couple of basic operating system pieces, technologies that have been around in Linux for a long time. One of those is called the Union file system. And the Union file system basically allows you to stack different file system layers together and to be able to kind of drill down through them to be able to access things. So in this case, if we actually wanted to, let's say we have files at different layers here. As we built up these layers, as we did the steps in the Docker file, we got files that were different layers here. Now, if we want to be able to access those, the Union file system allows us to kind of look from the top down. And again, a similar way to sort of the path environment variable. If you have the path set up, you know that you have a set of directories that are chained together. If you don't find something in one, you go on to the next one. If you don't find it there, you go on next one. Similar idea with the Union file system. Of course, that brings up the point, though. What happens if I need to actually modify something in one of these files? Well, the way that works is that Docker and other applications have this idea of copy on write, or CAL for short. So if I need to, let's say, modify the file shown here in brown down the lower level layers, we said that these layers are immutable, they're read only. So how do I do that? Well, what happens is when you need to write something to it, the underlying system can bring a copy of that file, or put a copy of that file up in the container layer. The container layer is that read-write layer, so we can actually write things in there. And because we're using Union file system, when we put a copy of that file at that top layer, that's the one that's seen first. So it blocks it from being seen further down. So in this case, we can make all the changes we want at that container layer in our container without having to change the underlying files, underlying structure underneath it in the lower level layers. So this also, because we have this immutability, we have the images that are read-write layers here, or I'm sorry, that are read-only layers here. That means something else. That means that we can also spin up multiple containers based on the same image. If the image is that sort of self-contained, unchanging set of content, environment configuration, application, and such, then I can actually spin up any number of containers I want to based off of the same image by just having different read-write layers linked to that. And that's what this picture is showing on this slide. We have the different containers that are all based off of the same image. So I can create as many images as I want, or as many containers as I want, rather, without having to make duplications of the images. Now, it actually gets a little bit more, even more detailed than that, or more useful than that at lower levels. Because, as we said, the layers are actually contained in the operating system, stored in that Docker area as separate objects. So if we need to pull down another image that already uses some of the same layers, Docker doesn't have to go and get those same layers down twice. It's able to recognize that, oh, this image is using this layer with this ID, and I already have this layer stored locally, so I don't have to pull it down again. And that's what's being shown here in this lower section here. You can see I do a Docker pull of Debian, and then I try and get down to a certain number of the layers that make up the image. And then later on, I do a Docker pull of Debian Jesse in the bottom here, which pulls down the images again, or tries to pull down the image, but it says, hey, I've already got these layers existing. So again, the layers are individual units that are stored in the Docker area on disk. And if the layer already exists, it doesn't have to pull it again. It can just wire it in so that it's connected in if I want to create a new image based off of that same layer. Pardon me. So it also simplifies being able to run multiple containers, being able to reuse layers and images and so on. These layers are generally stored on your disk, usually in the area called var live Docker. And Docker uses different storage drivers to know how to weave these together and how to manage them. Because again, if you think of it kind of as being like the path, it's just kind of setting these all up in a certain, certain organization so that we can go from one to the other, and combined, they create our image, and then we put that thin layer on top. So the storage driver is what allows it to be able to know about which layers it has, which ones it does, and which ones it needs to pull down, and how to weave them together into images and create containers and so on. So we mentioned Docker quite a bit. What is Docker? Well, it's really an application for managing containers and images. And there's a little bit of the public relations speak here on this slide. But underneath it, it is really a thin wrapper around something called LXC, or Linux Container Technology. And Linux Container Technology has been around for a long time. There's basically sort of three parts. There's the Union File System. As we saw before, we can drill down from different layers and be able to see files that way. There is something called namespaces and control groups, which allow us to be able to, excuse me, folks, let me get a quick drink here. There are namespaces and control groups, which allow us to be able to partition off those operating system resources for particular applications, for particular images, so that the applications running inside and the images think they have their own system to run on. And Docker also then provides like a RESTful interface for the service, meaning a way to contact it through to be able to work with images, be able to create containers, provides a description format for containers, provides APIs to be able to access the functionality and so on. So Docker was really the first application to really put a structure around this. It didn't invent the technology in terms of the underlying technology that's been around for a long time, but Docker was the one who really put a structure around this, set a way to describe what the format structure of containers and images were, how to access them, and those pieces that made it easier to deal with. We mentioned the Union File System earlier, the other pieces of technology that it uses, a thing called control groups. Control groups, group processes for managing system resources. If you think of it, things like system resources being CPU, memory, IO, and network, a control group is a way of taking portions of these and allocating them for what of these containers to run with, to use in there, so that it has some memory to work with, CPU, IO, network, etc. Windows uses a variant called job objects, but it's the same idea. Basically, this is a way to share system resources among containers, as well as constraining them, because if you're running a container inside the system, you don't want applications inside of a container to be able to reach out and interact with applications in another container in a way that's not planned. Of course, you could have API calls and sending communication and networking back and forth, but you want to make sure that for purposes of that container, it appears to it that it has its own set of CPU, memory, IO, and network, etc. Another one is namespaces. This is an isolated instance of another global resource in there. So it allows a separate instance of resources within a certain namespace. So Windows uses a variant called silos, but these come in things like process IDs. If you think about an operating system has a lot of processes. They're all going to have unique IDs. When we start talking about running applications inside containers, those applications need to have their own unique IDs that are unique to within the container environment. The container environment, again, is sort of like that self-contained computer. So it needs to act as if it's the only processes that are concerned with. We also have things like networking, network controllers, system resources, firewalls, routing tables, all the pieces in there, mount points, file system mount points, IPCs, interprocess communications, message queues, and so on. Now, some of these terms may not mean a lot to you, but basically these are operating system structures that whereas if we're not running in containers, these are global to the whole operating system. But when we start using containers and cording off pieces of them, we need to have portions of these that we can give to the containers. So the containers basically think they have this kind of resource all to themselves. And time sharing service and user spaces as well. So we mentioned Docker files before, so I'll just go touch on this briefly again. Basically, the Docker file is a plan. It's kind of like a recipe or a plan for how to put together the image that we will eventually run as a container. And it has a specific format and structure here. And as we said, each instruction can create a read-only layer. And you can see a couple of examples here. In the one on the top, we start with a Tomcat image. Tomcat is a web server, and we have a particular version. And most times you'll see images in this kind of format. The application name followed by the tag identifying the version number 7.065, or in the case of MySQL 5.5.45. And the image version is how we differentiate the different versions. As these have newer versions come out, you'll typically see newer images provided that will have a different version number at the end. And then from there, it's just a matter of copying in files that we need, running configurations, running any other things we need to configure that environment for us. Going from a Docker file then to an image to a container, if we're using Docker itself, the Docker build command is what moves us from the Docker file set of instructions over to actually creating the image and then actually running that image to be a container. So the run command is what allows us to have that image be turned into a container simply by adding that read-write layer where the application can then run, create content, and so on. Docker commands, lots of Docker commands. We don't have time to go into all of them here, but you get the idea. There's a Docker build command to take the Docker file, turn it into an image. There are commands to show the images that you have on your system, Docker images. There are commands to remove an image, Docker RMI. You can pull an image from a registry, add a tag or identifier on it, and so forth. And Docker run, as we said, is the one that allows us to take an image and turn it into a container. So how do we think about all of this? Well, I mentioned this earlier, but I think the most useful analogy is to think about installing software on a machine or provisioning a system for users. Again, if you ever had to do this for a family member, or maybe it's part of your job at work, this will be familiar to you. But if you think about taking a blank computer and sitting there and installing the different layers of software, like the operating system, maybe some office applications, antivirus, etc. I'm not saying these are all the kinds of things you would put in an image, but just as an analogy. Once you're done with that, you have an image that you can take and store somewhere. And then if you ever need to provision a new machine with that software, you can take that same image and put it on that machine and have it available. Now, even if the machine's turned off, the software is still there, right? It's still configured, it's still set up and everything. But when you turn it on, if you then need to be able to have somebody use it, you would typically create a user area, right? A user area, home directory, those kinds of things, a place for someone to work. That's the place where they're going to be contained and they're going to do their different activities. They're not going to be going in and modifying things in the underlying operating system where the programs are installed and such. So we create that user area. Likewise, we use that same image to create another computer. We could just put the software on there by just having that image available with everything all set up, and we could create another area, home area on that computer for somebody to work. So we can think about then the image as being like a Docker image. It's that set of content, provision set up and configured for use. And the container as being like actually turning on the computer, creating that space where you can modify things and update things and so forth in there. That's an analogy I think that's useful. Hopefully it'll be useful to you as well. So Docker on Windows and Mac. So we said that Docker or the containers are largely based on Linux container functionality or LXC. On a development system, user runs Docker at the host. On Linux or Mac, the host is Linux based, so we can leverage those functionalities from the Linux system. On a Docker desktop or on Windows and Mac, there is an application known as Docker Desktop, which hosts containers in a development environment provide some additional tools. Now, a lot of times in the past, what they would do is they would have Linux virtual machines that ran on Windows, and you would basically be using a virtual machine running Linux to do containers, because containers were simply based on Linux technologies. Windows containers, though, have evolved, and they've gotten to where they have different kinds of runtime environments where they can do more of their own kind of native containers on there. There's a couple of different types of runtimes they use. Looking at the bottom of the slide here, Windows Server containers, which use some process and namespace isolation, and what we call Hyper-V containers, runs each container again in a VM. So where Windows didn't originally have containers, they typically relied on running a Linux virtual machine to provide that environment for creating images, containers, and so forth. But now they have moved forward and actually have a sort of Windows native containers. Reviews on that are kind of mixed, I would say. I think the jury is still out, as they say, on whether or not that's ultimately going to be a good thing or not. But Docker Desktop does provide a good environment. So if you need to work on Windows and you need to run with Docker, you need to work with Docker, I'd recommend the Docker Desktop application. So let's dive just a little bit, in a few minutes we have left, deeper into layers here. So as we said, containers can reuse layers. So Docker commands, if they can reuse the layers, they already exist. So if I pull down Alpine, for example, I'll pull down a layer from there. And then later on, if I pull down Alpine/Helm, Alpine is a very minimal operating system, and pull means to get it from the public Docker registry, that repository for Docker images. If I pull down Alpine Helm on the same machine, then if I've already got one of the layers there that I need, Docker doesn't have to keep it, doesn't have to pull it down again. It just pulls the others down. And layers themselves, we've seen these kind of funny names in the layers. You may have noticed a string of characters and such. So a layer, though, and we talk about this as the way it's stored in the operating system, the way it's mapped, it's really just the difference when commands are run from the image build process to produce the changed files. You may recall from when we saw the Docker file earlier, we started with a layer that was based on an existing image that we pulled down, the basic operating system. Then we had another layer where we made changes. We copied files over from a local area to put on it. That became a new layer. So each layer becomes a difference or a delta of what was done before. Prior to Docker version 1.10, images and layers were kind of synonymous. What we mean by that is that if you were to look at the layers in an image, you would see that they actually mapped directly to a directory that was stored on the operating system. So if you were to look at what was in an image, like doing a Docker history or something, you could see, oh, that image there, that identifier actually mapped to a directory out of my Docker space. And I can do a Docker inspect, which allows me to see some of the other metadata about the actual things that have gone into the image. But in 1.10 plus, Docker version 1.10, they realized there were some challenges with this. Basically, security. If you were trying to figure out if an image was tampered with during a push-pull or whatever, because it was just the same directory name, it was hard to tell if somebody had just messed with the contents inside of the directory. So they added this new approach called content addressable IDs. What this really means, they just did a hash. They did a hash or checksum, you want to think of it that way, for computing the name or for giving these layers name. So basically, if you were to look at the layers in the operating system now, the directories where they're stored would be with a checksum value. So that means that you can't really change the content without changing that checksum. So that's what we talk about here in terms of the digest, if you see the digest. So if you were to look at what went into an image now with current versions of Docker, you would see different layers which have this digest or this checksum in there. So let's talk a little bit about storage drivers. So if you're wondering, just this is getting a little bit deeper into kind of how Docker works, but I think it's worthwhile even when you're starting out, because I think it's easier to understand when you start to spend a little bit of time just relating how things work, how they're actually implemented. I won't try to go too deep into this, but we said that a Docker engine or images are made up of layers. So when you have Docker installed on your machine, out into the area where Docker is installed, typically var live Docker, somewhere like that, you'll have the different directories, and those directories represent the layers and their various contents. Layers come from Docker pool, getting them down, or Docker build, building layers, and so forth. And the driver or the application that we have on the system that allows us to manage the layers at runtime is a storage driver. And the storage driver is that piece that knows how to kind of combine the layers together to form the images, startup containers, and so forth. Lots of different
Brent,
storage drivers. Yeah.
sorry to cut in, but just let you know we have 5 minutes left.
Okay. Let me run through this and I'll try to see if we can get through some questions. So I'll try to be quick
That's
about this.
that's good because at the moment we don't have any questions.
Okay. All right. So storage drivers here, there's been a number of different storage drivers you may see used or talked about in terms of Docker. I won't go into all these now. Basically, the one that's used now is what we call an overlay. And it's simply a matter of, again, combining those directories together so that you can weave your way through them, much like a path variable where you're combining them together. In fact, you can see kind of down here on this command, there's you can actually, if you were familiar with Linux, you could mount these and you can have an overlay where you have different levels of directories combined together in there, and then you can drill down through them. To give you a kind of a visual of this, what we call the overlay model, basically it takes layers from where Docker stores them and combines them together, stacks them together. And we have a base layer, and then we have an upper layer and another layer on top of that. And so you can kind of get to see this drill down model here. And if you actually delete a file, you just put it, basically what it does is puts a blockout file, or what we call a whiteout file, in there so that it kind of hides the files at a lower level. So that's what's going on. So when you look at a Docker image or a container running things in there, what you're really seeing is you're seeing that sort of view of looking down through the layers to be able to access content. You can get information about what driver Docker is using things like Docker info. It'll tell you which storage it is, which overlay driver, and it'll also give you information about where things are stored on your system. And if you wanted to look in your system, you could actually look in and find where the pieces of Docker are stored and managed in there. So real quick note about Docker alternatives. Used to be that Docker was really the only game in town in terms of containers. People pretty much thought of them as synonymous. But these days, there are a lot of other contenders out there to work with it. What has happened is that back in 2015, Docker worked with the Linux Foundation to actually create this, what we call Open Container Initiative, OCI. You'll hear this OCI term around a lot. All this really means is that there's a standard now. What Docker did is it said, shared back and said, here's the way that we structure things. Here's the way we put images together. Here's the way we access things. And so it made its specification more open source. So now any application that works that will work with OCI or wants to can work with images and containers. And you'll see there are several others out there, Podman, Builda, Kaneko, all have their own sort of nuances and specialties in there. But the point of this is that Docker is no longer the only game in town. Basically, you can, sorry, folks, you can use these other things, and as long as they're OCI compliant, they can be used like Docker too. Again, they all have their own nuances and specialties in there. Real quickly, Docker security. So one of the problems long-term with Docker has been that it required root access to actually build images and work with processes. So when it did that, that was a problem because giving something root access has been an issue. That's another reason for the rise of these other applications and alternatives to it. As of version 1903, there is a rootless mode available, which kind of helps to mitigate that. But that's the reason why, another reason we have the Open Container Initiative is it is something that is able to allow these other applications to work with them so you don't have to risk some of the security problems with Docker. And we have time to go into these other applications, but I've got a couple of slides here on these other ones about what they're used for. All right, so I see we're out of time, so I'll finish up there. think we've got one question. Do you have to use sudo to create the image layers in a container? Is it possible to set up a super user to run these types of commands? If you're talking about Docker, Elizabeth, basically, if you're not using the rootless mode, the newer rootless mode, Docker is going to require the root access to be able to build up the images in there. You don't, if you install Docker, you don't have to use sudo. You would need to make sure it has the access permissions for the groups and that sort of thing, but you don't have to use sudo with it. So. All right. Any other questions, comments? I know that was a lot of material to throw your way. Part of this, again, though, is just to kind of give you the big picture of this and also give you a little bit of the depth of it. I hope this was useful to you. Not sure, Kiana, do we have any other questions that I've missed?
No, I don't see any additional ones.
Okay. All right. Well, we'll make the slides available, folks. Again, a lot of information, but I hope that it's been useful to you, and I hope I get to talk to you again in a future class, maybe open source 101 or maybe on O'Reilly or somewhere. Thank you all.